Looks like we got a little geometry review here.
Yeah, we're starting to do ACT stuff, and
good.
I kind of thought about this stuff.
That's a good reason to review, because a lot of people have been a year or two since you took geometry, and there's a lot of geometry on ACT, so it's good to review. Which is the first page? Is it this one or this one?
They're both the same page. It's just two different sets of problems I don't get.
Okay. So we got these three problems at the bottom.
Yeah. And then the three that are in an X, another one. Or that are X'd out with red pen.
Okay. All right. Now we start with number 4.
All right.
I haven't looked at any of them yet. Let's see. All right. That's a right angle, 90 degrees. And they want to know the length from A to B, the arc length. What's the length of the circumference? First of all, what's the formula for circumference?
Isn't it?
Let's look at area and circumference. These are two things that you want to know, like your name. Area is pi r squared. Circumference is what?
2 pi r?
Yeah, same three numbers, only arranged differently. So what's the circumference of that whole circle?
Which be, because you plug it in for 6 and for r, so it'd be
Right.
2 pi 6. No, would that be 12 pi?
So 12 pi is the circumference of the whole circle. What percentage of the circle are we talking about when we look at
25%.
arc AB?
25%.
What's 25% of 12 pi?
3.
There's your answer.
Okay.
Whatever this angle is, if that angle was 91 degrees, then it would be 91 divided by 360 times 12 pi. Okay? Since it's exactly 90, it's exactly 1/4 of the circle. But it wouldn't have to be. Whatever percentage this angle is of 360, you get it that way, then that's how you do that. All right, let's see. Let's look at this next one here. The next red X. Circles are pretty good today. I don't usually draw circles this good. What's this angle right there? I'm not sure it's even pertinent. I haven't read the problem yet. But it's important to know. When you put a triangle in a half of a circle, that's always 90 degrees. Whether it's drawn like that or like this, that's always 90 degrees. Key principle in geometry. Now let's look at the problem a little bit more. let's see, they said that this angle, I can't read that, does that say 30?
Yes.
Well, what kind of triangle is that then?
30, 60, 90.
And what is 12 inches? Let's see, if BC, this is 12 here.
Yeah.
What's the radius of the circle in inches? So there's the diameter of the circle. Let's review our 30-60 triangle. I like to call this a unit 30-60 triangle. Most everybody uses these dimensions. Okay, so what we're doing here is comparing similar triangles, right?
Yep.
In other words, this is the hypotenuse of the triangle and the circle. And the side opposite 30 degrees is 12. So what is the similarity ratio? By that I mean how much, and I hesitate to even say this, how much bigger is this triangle than this triangle? And when I say how much bigger, I don't mean the area, I mean corresponding sides.
So 12.
12 to 1. Right? In other words, every side of this triangle here has to be 12 times bigger, not 12, yes, excuse me, 12 times bigger than this triangle. Therefore, what is the hypotenuse of this triangle?
36.
It's 12 times 2.
Square root of the... Oh.
Make sure you get the right side. In other words, the key to these similar triangle problems is, notice this isn't oriented anywhere near the same as that's oriented. They're both 30, 60, 90 triangles, and they are similar, but you have to match up correct sides. Now, up here, we can see that the side opposite the 30 is 12. Well, down here, the side opposite the 30 is 1. So that's where you get your similarity ratio of 12 to 1. Well, that means every side has to have that same similarity ratio. So if this side opposite the right angle, or the hypotenuse, is 2, what's this side up here?
So it's just 24.
Yes. So the diameter is 24. What's the radius?
12.
That's the answer. All right. Let's look at this one here. In the figure, and they don't give us a lot about this figure. All right, let's see. That angle is 40. This little tiny angle is 20. This angle is 70. This angle is 110. And this angle is x. So, with these kind of problems, and this is classic ACT problem. Your ACT geometry problems, you can almost never solve for x immediately. Notice I cannot solve for x until I figure out what that angle is right there. Once I figure out the check-boxed angle, then I'll be able to solve for x, right? In
Yeah.
other words, the key is that the sum of all the angles are 180. So, there's always other angles you have to solve for before you can solve for x. I can't even imagine they would give you a geometry problem like this and say, this is 90, this is 70, what's that? That's just too simple. None of their geometry problems are going to be that straightforward. Every one of them, you're going to have to solve for another angle or two first. So, what can we solve for? Do we know this angle?
Yeah, 70.
All right. Now let's look at the triangle on the left. Do we know that entire angle?
Once you add the 40 and 70 and 20 together, then you just subtract
Forget the
that.
20 for a moment.
No.
Just let's look at that whole corner angle there. This whole, the thing that I've circled is the third angle in this triangle on the left. So what must that whole angle be worth or be valued at?
70.
Correct. In other words, we're looking at a triangle that's a 70, 40, 70. Okay? Now that I know that this whole thing is 70, what is this little angle right here? The third angle on the bigger triangle.
50.
Okay? Now that I know that's 50, what is x?
60.
That's the way you do all of these geometry problems. You just start, in other words, we actually had to solve this angle, 1, and we had to solve this angle, 2, and then we had to solve this angle, 3, before we could solve for x. So we actually had to solve for 3 other angles first. And that's just the way to proceed on these geometry problems. They're all pretty much based on the fact that 180 is the magic number. 180 is the sum of all angles in a triangle. 180 is also the sum of, not, what do you call those? I can't think of the name right off. But whenever you have a straight line, these two angles, A and B, are always supplementary. They always add to 180. And that's how we got 70 there. Okay?
All right.
All right, let's go to your other page. That was all that's on this page? That
Yeah.
we had to deal with?
Yeah, that's all our problem.
All right. So let's look at these bottom 3 problems. A rhombus is a parallelogram with sides of equal length. In the figure below, ABCD is a rhombus, and EBC is 34 degrees. What's the measure of angle BDA? This angle right here. So all I can say is that it's a good thing they don't have 34 degrees on there as an answer, right?
Yeah.
Because that's what we would have picked. It looks like it's 34 degrees visually, but it isn't. Clearly from answers. Those 2 lines are parallel. These 2 lines are parallel. Parallel being the key. on the ACT test, you absolutely have to know your equations and your parallel lines. Okay? So that's 34. What other angle, if I label this thing A, B, C, D, what other angles can we determine?
We can find B.
Okay. B is what?
Subtracting 146.
Okay. What else do we know?
And then the one just below B is 34, and then
Okay, so that's 34, and that's 146 there. What's angle D?
would that be 146 again?
Yes. Because opposite angles of a parallelogram are equal. This is 34 because of the parallel lines, and those are corresponding angles. And therefore that's 34. So we've got the rhombus labeled. Now the question is what happens when we run a line like that?
Which divide 146 by 2?
Yeah, it does. Now, how do we know that? Think about this for a second.
Which create two triangles that each equal 180.
Well, we don't know for sure what that angle is. But what we do know for sure is that these are congruent triangles. In other words, that triangle and that triangle are congruent. And we know that when we draw a parallelogram, regardless of whether, no, let's see, if I drew a parallelogram like this, which is a parallelogram, but it's not a rhombus, that does not bisect that angle. And you can see that. If I make my parallelogram really, really long, it doesn't even come close to bisecting that angle. So the question is, when we have a parallelogram that is a rhombus, all four of these sides are equal, then that does bisect the angle, so does that. In other words, that's equal to that, and that's equal to that. I guess you just have to memorize that. Trying to figure out if there's another way we can be certain that that bisects it. I know 73 is the right answer. I guess it's just because of that principle with rhombuses. Not sure if we can use the parallel lines here to come up with that angle. I don't think so. No, you may just have to know that it bisects it. Similar to a square, which is also a rhombus, and if I draw diagonals on a square, that's 45, and that's 45. And same case with a rhombus. I'm not sure I can prove that a rhombus bisects those two angles with the diagonal. Not sure I need to prove it. You just need to know it. That's one of those things about geometry. Alright, let's look at this one. A rectangular wall of height h feet and width l feet is to be painted. There's our wall standing up of height h and length l. If the wall has 4 rectangular windows, each of height x and width w, what is the number of square feet to be painted? I'm going to put my 4 rectangular windows right there. Doesn't matter whether I line them up horizontally or put them, in fact it doesn't matter where I put them. Each of these walls has x by w. All 4 of them do. What's the square footage to be painted? In other words, this is a shaded area problem. Shaded area problems are always what kind of problems? They are always subtraction problems, exactly. In other words, we could go to a great deal of lengths to solve this whole thing by figuring out this distance here and what that area is, all 8 of these areas, but by far the easiest way to solve this problem is to take the what? The area of the outside rectangle and subtract the areas of the 4 inside. What's the area of the wall without the windows?
Length, width times height.
Which is?
H times L.
Okay, so LH is the area of the wall subtracting 4 times the area of each window, which is what?
XW.
There's the answer we're looking for right there. Is that on there?
Yeah.
H. This is kind of an unusual shaded area problem because we actually could figure out the area if we did it the hard way. In other words, we could figure out this area, and we could figure out this area, and we could figure out this area, and this area. In other words, we have the geometry to figure out all those areas. Not that it would be easy, but we could do it. That's not a typical shaded region problem. A typical shaded region problem is one that you can only solve by subtraction. If I wanted the shaded region, I don't have the geometry. You have not yet been taught the geometry to figure out how to do it if it's inside of a circle like this. The only way to get the shaded region for this problem right here that I've drawn is the area of the circle minus the area of the rectangle that's inside the circle. That would give you the shaded area. And this is a more typical one because we don't have any other way to solve that one. This might be harder because some people might go about this and try to do it the difficult way. If I gave you this problem here, you wouldn't even attempt to try to do it the difficult way because you don't have the geometry for doing that. But we can certainly do it the easy way. We know the areas of circles and we know the areas of rectangles. Ah, look at this. Almost the exact problem. Only it's a circle inside of, what is that shape right there?
a square.
Has to be, right?
Yeah.
Can't be just a rectangle. All four sides are equal. So the circle inscribed in the square has a radius of 2 inches. Make it tough. What's the area of the shaded region in square inches? Shaded region being this. So in terms of the square and the circle, the shaded region is what?
It should be area of the square minus the area of the circle.
Okay, what's the area of the square?
4.
What's the side length of a square?
Oh, the side length 4, so 16.
What's the area of the circle?
It's 2 squared, so it'd be 4 pi. Alright.
These are all good geometry problems that are absolutely typical of what you'd find on the ACT or the SAT. So these are ones you want to know how to do for sure.
All right.
Okay? All right, Mitch, I will talk to you, I guess, next Monday.
All right. Thank you.
You're welcome.